Hello, everybody. We're going to talk about hypothesis testing for two samples, and we're going to talk about the hypothesis testing of means. But in this case, we're going to deal with dependent samples. What does that mean? Well, let's look at an example. We have this 2011 study, and we're looking to see if there's evidence, i.e., that judging of quality is significantly different from self-purchases than other purchases. And so what we did was, in this study, if you want to believe it, is you have a self-purchase column, and you have the other purchase column, and you have data. You have data 1 over here. I shouldn't use D because I'm going to use that later. You're going to have data 1 over here, data point 2 over here, data point 3, and it's going to go down. The same thing over here, you're going to have data point 1, data point 2, data point 3, and it's going to go down. Now, if they're paired, if you can match them, matching them being you're voting on the exact same purchase, in this case, matching on the exact same purchase, matching on the exact same purchase, just the difference is your rating versus your friend's rating. That's really what you're looking at. Your rating versus your friend's rating on the exact same object. Your rating versus your friend's rating. All right, so since they're matched, and that's very important, since they are matched or dependent, so we are matching things, then what we can do is create a third variable called the difference variable, big D. And the difference variable is what you would think it is. It is x1 minus y1, x2 minus y2. You're just subtracting the values of whatever x1 and y1 are, and it goes down. So what you've created is this new column of data called the difference column. That's the data I'm going to look at. This difference column, I'm going to look at these numbers. Now, if there's truly no difference, then down this column, down this main column, all I should see is a bunch of zeros or a bunch of numbers close to zero. If these numbers stack up to be too positive or too negative, then there is a big difference between the two sets I'm looking at. If this difference is close to zero, then I would say the opinions of the left and the right are very similar. And that's the tactic we're going to take here. So what happens is, in this question, they've already gone and taken a look at 36 participants, your vote against their vote, and they found the average difference to be 2.8 points. So according to my formula sheet, and that's where I want to start, actually, let me pause. I don't want to go too fast. I want to recall a formula we're going to utilize later. Sample variance, S squared, is SS over n minus 1. I'm going to keep that in mind, that S squared is equal to sum of squares divided by n minus 1. That'll be a recall for a formula. What I want to do on our formula sheet, give you a chance to look at it, and maybe pause the video and take a look at it again, is we're doing a hypothesis test. And we got to be clear, it's a hypothesis test, not with two independent samples, nope. But we have a hypothesis test with two related or matched samples. And if that's true, this is the set of rules we'll follow. That is, we're going to follow the T statistic, and the average difference of your between group compared to the average difference of what your suspected is what you're measuring. So MD is actually the mean difference of your samples. MD is the mean difference of your samples. If you read the question, again, it states we sampled 36 participants and found the average difference. So, first of all, they said they sampled 36 participants. That's N, of course, right? N is always the sample size. Now, MD, the mean difference of the group, is what they found there. They found the average difference to be 2.8 points. Please understand, in a hypothesis test, mu sub D is usually 0. We assume that the average difference is 0. That's what we're assuming. The true average, remember mu, Greek letter mu stands for the true average difference is 0. MD is the sample mean difference, Greek letter, not Greek letter, American letter for the sample mean difference. So the question is 2.8 that far from 0? Well, I don't know. What I need to do this correctly to get the test statistic, because that's going to measure it, is I need to know SMD, the standard error of the mean difference. The standard error of the mean difference. That's what I need. The standard error of the mean difference. So I need the standard error of the mean difference. The problem is the standard error of the mean difference relies on S, the standard deviation, and N, if you look at the formula. Look at the formula again. SMD, the standard error of the mean difference, relies on the standard error, and that's the standard error of the pairing, divided by the square root of N. Well, we don't have S, okay? In fact, what we have is SS, sum of squares. And we don't need N again because it ends up here. So we don't need N again, so let me get rid of that. See, SMD is equal to S, the standard deviation of the difference, divided by the square root of the sample size. And we're not going to have a number there because we don't know what S is. But S, by definition, let's go back to the formula sheet here. Can I solve for S? Yes, I can find S. S will equal the square root of SS divided by N minus 1. From that formula I took from the formula sheet, that the sample variance is equal to the sum of squares divided by N minus 1. So the sample standard deviation, or the sample error, will always be the square root of SS over N minus 1. So let's go back to the question. This is a lot of reading and understanding your vocab. See, they gave us the SS, the sum of squares, okay? They gave us the sum of squares. Read the question. The sum of squares is 135. From the sum of squares, can I get to little s? Yes, by the formula I just showed you. It's the square root of SS, I gotta be careful writing it, divided by N minus 1. So 35 in this example, right? I'm going to write it in Excel as parentheses this minus 1. You need the parentheses in order to activate the minus 1. Got to be careful, and so I'm pausing there, and you should pause there to see that formula. It is G6, which is the sum of squares, divided by, you got to have parentheses around that N there, 36 minus 1, or 35. So there's your standard error, which leads us to the standard error of the mean difference to be 0.327. Everything kind of has its place when you're doing the math. I noticed they had the sum of squares. Sum of squares leads me to the standard error. Standard error leads me to the standard error of the mean difference, which is what I want. Each one of these has a formula, and they kind of work together to get me to the standard error of the mean difference. Why do I want that? Well, remember, we're doing a hypothesis test. This is there evidence? This is all the setup I'm going to do the hypothesis test. Now that I got the setup done, let's go through this slowly, the hypothesis test. So the hypothesis test for this example, we start out with H0. What's H0? Well, H0 is the average difference, the true difference, that's mu, the Greek letter difference, is 0. We're going to test to see if it's, well, let me read, make sure it's not one-sided, it is different from. So the question says different from, so that's a two-tailed test. All right, guys, it does say different from. If it said more than, I do a greater than. If it said a less than, I do a less than. I have to read the question. It said different from. We're wondering if our opinions are any different than our friend's opinion when we buy the same product. That's it, guys. It's all based on perception of yours versus somebody else buying the product. You bought the product, your friends bought the product. When you perceive perception based on you buying the product or your friend buying the product, is there a difference? We're going to naturally say, no, there's no difference. You have to show me there's a difference. How do you show me the difference? Well, again, we're going to need our alpha, our level of significance. Back to the question. It said 5% level of significance. I guess that should be in the pile of data here, right? Alpha is 0.05. That'll help us when we do our work. Alpha is 0.05. So we have H0, H1, and alpha. That's typically good for this. Now what happens? Well, now you need your test statistic. And it is a t-statistic. Why is it a t-statistic? Well, because we're basing our data on a sample. And that plus the formula says it's a t-statistic. It's MD minus mu D over SMD. All right? What is SMD? It's S over radical N. So you can shove that right into here if you don't want to look at that. So my formula, if you're a fan of formula, is MD minus mu D over S over radical N. Now, what is MD? That's the mean difference going back to the beginning. That is, if you had two sets of data, first thing I would do is subtract them to create this new variable D that you're seeing all down through here, D. The average of this column is what I'm looking for, the average of this column. The average, all right, the average of this set, the average of this sample is M sub D. And so MD is the average of the sample. We were given that average. We said, or in our sample, our average difference was 2.8. We're comparing it to 0. Why? Because that's what we're assuming. Mu D is 0. Notice that, mu D. Mu D is 0. And yes, we always assume mu D is 0. There are very rare cases you don't, but almost always we assume mu D is 0. So you often just see a 0 back there because that's what we're assuming. Now what's S over radical N? Well, S over radical N, S is the standard error. They didn't give me the standard error. They gave me the sum of squares. That's why I needed a little reviewer knowledge right here. The standard deviation is equal to the sum of squares divided by n minus 1. Luck would have us, they gave us the sum of squares, and we know what n minus 1 is, so we just crank that formula out. If you don't like Excel, right, you could just write the formula. We know that S is equal to a radical sum of squares over n minus 1. In this case, sum of squares, I believe, was 135, right? Sum of squares was 135. Sum of squares was 135. N is 36, so n minus 1 would be 35. And we just cracked that out in a calculator, and we better get the same thing you see there, 1.96. Now that we have that, we can put that back into the master formula, dividing this by square root of 36 for the n. This number better be the t-stat. If you do it by hand, well, we haven't plugged it in yet, right? We haven't plugged that in. I apologize. So we now need the t-stat, right? Well, the t-stat is equal to what? One more time. It's equal to your average minus national average. That's the way the numerator always is. Your sample average minus the national average. In this case, we're assuming the study is 0 because we're assuming there's no difference. Divided by the denominator. The denominator is the error, that's the S, the standard error of the mean difference. That number right there. And so if you do the work out over here, you should, if you do this math out carefully, and you got to do the denominator first, you would get 8.55. So my T statistic is 8.55. I'm going to let you know, I don't have to do much more other than realize the fact that that's huge. All right, that is well over 3 standard deviations away from average. So that means I'm probably going to reject no matter what alpha somebody brings to me. All right, this is a very significant t-stat. But let's continue on, because after you find your statistic, you should find your critical value. I don't know what they're going to ask you on any homework, on any research project. I just give you all the information, and you need to figure out what pieces you need. I give you all the steps, a complete hypothesis test. All right, sometimes we cheat and only do a few steps. So the first thing you always do is you write down your no, your alternative, and your alpha. From here, you crack out your test statistic. From there, you build a critical value. Well, the critical value is based on the t-statistic. Why? Because you got to follow suit with your t-stat here. So your critical value is based on the t-statistic. I'm going to do 2 bars because that's a not equal to an alpha. Remember, recall from our previous videos. Alpha will be the shared area outside. So that's 0.025 on both sides. Since alpha is 5%, we cut it in half and do 2.5 on both sides. The critical value is this number. And by the way, they're the same number, just opposites in sign. So if I can find this number in the t-tables, then I can find this number by symmetry. So how do I find this number? Again, you can utilize your t-tables, or I like to use my Excel. I'm going to use t.inverse because that's how I always find my critical values. My critical values are always found by dot inverse. You got to just know how to use them. So the t-inverse always works with area below. That is, it's going to want this area below. You need that number. Well, that number, just think about it. How much area is below this bar? Well, if 2.5 is above it, then 97.5 is below it. 97.5 is below it. And of course, I just made a mistake. If you don't put it in decimal form, Excel will be unhappy with you. So 0.975. Then you need degrees of freedom, which recall is n minus 1, and then you're good. Remember, you need degrees of freedom because you need to tell exactly which t curve it is. See, when you use norm S inverse, there's only one Z curve. There are infinitely many T curves, and that's why I always need N minus 1. So I'm going to import that code into Excel. So that way it's critical value time. So to find the critical value, I'm going to use T dot inverse, and the probability will be, what do we say, 0.975, comma, degrees of freedom. Well, degrees of freedom is N minus 1, so I can put that in there. Boom. And so there's my critical value. Pretty good critical value, 203. So that means this bar right here is at 203 and negative 203. And here's what happens. Bottom line, if you fall in here, you do not reject. This is the do not reject region. If you fall here, you reject. And what I mean by reject is you reject H naught. If you fall here, you reject H naught. And that's what you're waiting for. You're going to collect your sample and see if your sample falls too far away from center. We already know it does. There's your sample. That's your number. Your number is 855. That's well into the rejection region. So we're clearly going to reject, and that's it. That's it. We're clearly going to reject, and we're done. Done with the story. If you did the critical value approach. Cool. We've just rejected, and we now know we have significant evidence to say that our opinion is different than other people's opinion when it comes to negotiating prices. But of course, some people don't like the critical value approach. Some people like the p-value approach. No big deal. The p-value approach, what do you do? Well, once again, you draw the t-curve, 2 bars because it's a not equal to test. In a p-value approach, you pick your number. Take your number, 855, and put it down on both sides because it's a two-sided test. The p-value by definition is the area more extreme than your value. So the p-value is the purple area I've shaded. That's the p-value. I got to figure out how to find the p-value. That is the area outside of 855 and negative 855. How do I do that? Well, if you've watched my previous videos, you'll understand how I always do it. I take twice because there's 2 areas and they're symmetrically the same. I like to find the area above the 855. That's just me. So I like to find the area above that. So let me think about that. How am I going to find the area above 0.855, the z value there? Sorry, the t value. Got the wrong words. I'm going to find t dot dist. See, dot dist finds the area below a t value. The area below a t value can be found by t dot dist. Again, t dot dist finds area or probability below. Remember, if you're going to use t dot dist, you need to have degrees of freedom lined up and comma 1 to let it know to integrate. You will always have a comma 1 or true back there statement, okay? Degrees of freedom is n minus 1. Now see what t-dist does, it says, ooh, you give me the bar, I'll find the area below. Understand, that's not what I want. Again, t-dist finds the area below. So if I want the area above, I'm going to do 1 minus. And that's how I tweak it to get my right answer. Multiply by 2 gives me both sides. And so that's what I'm going to type into Excel for this question. So the p-value is equal to 2 times, parentheses 1 minus t dot dist. My value, where's my t statistic? There it is. Comma, degrees of freedom. Degrees of freedom is n minus 1. Comma, always true. I'm just pausing to give you a chance to catch up with me writing. Again, why t-dist? T-dist gives you the area below the statistic. Got it. 1 minus then will give you the area above. Why double? Because we're at a two-tail. And I expect this to be a really small number. You might as well say this is, for all practices, this is practically 0. All right, guys? That number, E negative 10, means 10 decimal places you're going to move. That means we're practically 0. And that's important. But, so let's go through our rules, our results, to finish this bad boy off. What do I notice about my t-stat in my critical value? I notice that my t-stat is greater than my critical value. If your t-statistic is greater than your critical value, you will reject H naught. What else do I notice? My p-value, is under alpha. What does that mean? I reject H naught. Yes, both conclusions should say the same thing. Let me add a line here. Insert. Since I'm rejecting both, what does that mean? Well, when you reject, remember you're rejecting the null. Your null here was right here, that the average was 0. You're rejecting that, which means you have evidence that the difference is non-zero. There's clearly a preference in one direction or the other, and we'd have to figure out which preference that is. But there's clearly a preference. There's clearly a difference between self-purchases and other purchases and how you rate them. Excellent. By the way, even though this is done, this is awesome. As you know now from my previous videos, I often like to include a couple of other things. And I'm adding steps because I want them in there. That is, I would love to have the Cohen's d in there to make sure that sample size was not an issue. And I also like to talk about the 95% CI. You know I like that. And so I'm going to need another line. Well, I can do it over here. I'm going to need the error, lower bound, and upper bound. Especially if I reject. I like to, as soon as I know I reject, build a confidence interval to figure out where the true difference lies. But first, let's look at Cohen's d. I want to make sure that sample size was not an issue, that there is a large effect size. What is Cohen's d? Well, you go read. Cohen's d is the absolute value of the mean difference divided by S. All right, that's Cohen's d in this case. Please pause the video, take a look at your formula sheet. All right, take a picture if you need to. And there, by the way, here's the confidence interval I'll be using shortly. So they're both here. D, Cohen's d is the mean d over S. Absolute value. So equals absolute value is the mean difference divided by S. Notice we're getting rid of the use of sample size here. So the mean difference is 1.42. That's the Cohen's d measurement, is 1.42. Good news is I like to have a complete formula sheet up here. If the d value is over 0.8, we do not have an issue with sample size. That's awesome. So if we're over 1.42, we have no issue with the sample size. What does that mean? Effect size is large, and that's awesome. It's always good to have an effect size that's large, to have a Cohen's d measure above 0.8. That means sample size did not influence your result. All right, let's talk about margin of error. Well, margin of error is the back end of any confidence interval, period. Margin of error, E, is the back end of the confidence interval. In this case, is T times SMD. Is T times SMD. All right, guys? So we got to be careful, though. T dot inverse. That's how you build a confidence interval. When you're doing a 95% confidence interval, that means 95% is in between two numbers. What numbers is it in between? The answer is 0.025 and 0.975. You need to think about why I know it's 0.975 for a 95% confidence interval. Here's a hint. It's always 0.975. And then it's n minus 1 for degrees of freedom. So that'll be the t value. That's times, let's look at the formula one more time, times SMD. Well, good news. Here's SMD. And so there's your margin of error. And so what would be the lower bound? The lower bound would be equal to your value. It's always your value in a confidence interval minus the error. So that's the lowest the difference would be. 2 points. There's a low point of 2.1 difference points. What's the worst case scenario? What's the upper bound? It would be yours plus the margin of error. So with 95% confidence, I believe the judging quality is off between 2.1 and 3.4 points. That's what I know for sure. All right, guys, I want to pause here, but please understand, this information here is what comes in reports, all right? Let's just get straight to the nitty-gritty. This is what comes in reports. This comes, and the computer does it, dumps it all out. Not often do you have to do this part, all right? And you'll see that in our third example. But I want to show you guys how you could go into the nitty-gritty and get the results so you have a better understanding of what's going on. Bottom line, if your t-stat is above the critical value, and if your p-value is less than alpha, you reject. What does it mean to reject? What it means is you have evidence that this isn't true anymore, which means you believe the alternative. And if it's not equal, that means it must not be equal. That means there must be some preference between. And so the question is, where is the preference? Well, that's where you build the confidence interval. You could say you have a 95% confidence that the preference is a 2 to 3. What does that mean? Well, we got to know what your first group was. The first group is yourself. The second group is the other, okay? The first group is you. The second group is the other. So clearly, you inflate your quality. You inflate your quality. Well, that makes sense. We often have a self-inflated being. So we inflate our quality where if somebody else buys it, oh, okay, somebody else bought it. So you often inflate your quality by 2 to 3 measurable points. And that's what this study got to. All right, guys, I'm going to pause. I want you guys to try this out. Please, the biggest difference here, I'm just going to copy and paste this down, by the way. The biggest difference is we're doing a greater than test. So please keep that in mind as you work through the math. Hello, everybody. So, example 2. I've already done it out over here, but I want to walk you through it quickly. So what are we looking at? The belief that antioxidants improve an adult's cognitive ability. All right, let's do a study then. Let's do a pre and post like you would do here. That's a matched pair. Same exact participant, right? Just a month later, take the same test. And so we found the mean difference to be 7.2. Got it. Mean difference. That's the sample. We found the sum of squares to be 1215. Good news, once you have the sum of squares, it gives me the S, which gives me the SMD, the error of the mean difference. Yes, you do need a sample size. They did say where is it? We're going to pick 49 random adults. Got it. The hypothesis doesn't change here. That is the null. The null is I'm going to believe the difference, the antioxidants don't improve cognitive ability, right? That's our H now. I truly believe the true national brain won't change. We're expecting that it does. I got to be careful. So it won't be equals. It'll be less than an equal. Why is that? That's because whatever you pick for the alternative, the opposite must be in the null, always. So since I'm testing to see if it's greater than, more than, then I know the opposite, which is less than equal to, is up here. Alpha is 5%. All right, so what do? The first thing you're going to do is find your test statistic, which we found. Because the test statistic does not rely on the type of test. It's just a formula, which I've cracked out through all of this already by just copying and pasting that below. That's the great thing. Once you've done one right, you copy and paste and tweak as needed. The test statistic doesn't need tweaking. It's still the same, 10.02. Now I'm going to let you know this is even more extreme than the other one, so I know I'm rejecting quickly. All right. As soon as I saw a test statistic of 10.02, I knew I was rejecting. Let's go on, though. Let's actually look at the dirty deeds, the critical value. Well, this is important, guys. This is a more than test, so it's one-sided. Please understand that. More than one-sided, which means, using red here, these two pieces give me this. All of alpha goes up here. Please understand that. The previous one, we had to cut in half because I had 2 bars. Here I have 1 bar. And I want to find this area, no problem. I can find this area using T dot inverse. But you got to be understanding, T dot inverse only works with the area underneath. And the area underneath is 95%. If that's 5% above, then there's 95% below. And I did that in my Excel. I found T inverse 95%. Degrees of freedom n minus 1. I just happen to have alpha is 5%, and 1 minus 5% is 95%. So yes, my critical value is 168. And there's only one critical value. Let me make sure I got that right number. 1678. 1678. That's my critical value. Take your test statistic. Boom! Well into the critical region, well into the rejection region. I clearly have evidence that there's a difference. So that tells you antioxidants are clearly improving people's cognitive skills in their older ages, period. Awesome. Some people don't like critical values. They like p-values. They like to know how special their data set was. So what you do for a p-value is you take your number. That's very important. You don't take an artificial number. You take your number. Your statistic was 1002. And the p-value is this. That is the p-value. The area more extreme than your statistic. The area more extreme, the probability you can rerun the study and get the same result. How do I find that area? Well, I got to understand the t-distribution very well. To find that area, well, I would use t.dist of that number, comma degrees of freedom, because you got to pick the right curve, comma 1, to ensure that we always do the integral. That will find the area below. Please understand, t.dist, I don't know how many times I got to preach it, but t.dist finds the area below. That's why I do 1 minus for this type of example. And so that's what I have typed into Excel, and I'll just pause there to make sure I did. It is 1 minus t.dist of J17, which is the t-stat, comma, degrees of freedom, comma, true. Sweet. Now that I have all this information, and by the way, E negative 13 just means very, very small, close to 0, all right? That means 13 shifts to the left. That's scientific notation, if you're wondering. All right, what do we have here? Once again, my t-stat is bigger than critical value. Yes, so I reject. Once again, my p-value is less than alpha. Yes, so I reject. So that means I have evidence the difference is non-zero. So how big of a difference is it? Well, first, let's check out sample size. Is it an issue? No. By the way, the Cohen's d formula doesn't change. The Cohen's d formula does not care about left bound or right bound more than or less than. It just does a formula. And so 1.43, I love it because it's above 0.8, so no issue with sample size. Guess what? Your confidence interval is still good. Your confidence interval is built based on a two-sided 95%. So that's still good. Awesome. I love it when I could just utilize the same formulas over and over. I don't have to change much, to be honest. Really, the only things I changed are right there. These are what I have to change because it was a one-sided test. Same thing up here. Because it was a two-sided test, I had to be careful of those two numbers. These are just calculations. They don't care about one-sided or two-sided. The t-stat doesn't care about it either. Only the critical value and p-value care when it comes to deciding two-sided versus one-sided. Notice the difference. So I know there's clearly at least a 5-point difference on the cognitive scale, up to potentially an 8-point difference on the cognitive scale. Wow, great results here for this antioxidant test. Again, please understand, the reason why I got this in green is because that's what you see in the report. When somebody puts it to print out there in the research world, this is what they report. They may report the MD, they may report that, but they will report the results as is, right here. What the t-stat says, and so what the p-value and alpha say, and then they report the confidence interval to show you how big of a difference it is. All right, we could do the part B if you like, and I'll ask you to look at that. If we change it to a two-tailed test, do we change the results? Well, we could go back here, change this back to two-tailed test and see what happens. I got to believe it's not going to change the results much. That t-stat is so significant that it doesn't matter if you're looking at a greater than or not equal to test, you're going to reject. The only difference is where the critical value and the p-value are. In the end, it won't matter because my t-statistic is really, really significant. Cool. All right, guys, one more time. But this time with live data, all right? With live data. So a study in 2011 asked companies to evaluate factors that lead to motivated employees. At a 10% level of significance, is there evidence of a difference in the rating between global employees and U.S. employees? So let's look at the data. If I can click on it. There it is. So what we have are factors of people feel for well-being, all right? Well-being and working hard on their job. And we had ratings of global versus the U.S. And the question is, do you think the global, and I want to read it carefully. Oh, got to click back to the question. Do you think the global is different from? It's a two-tailed test. Is there a difference between the ratings between these two? Is there a difference between the ratings? That's a very good question. So I'd like to pause the video and I'd like you to try it out and see how you do. Now, You might be saying, how do I try it out if I don't have the data? Well, the data's here. You can pause the video and type it into Excel. Here's my big hint. Remember, to do Excel, you're going to need all the information we had before. That is the mean difference, the sum of squares, all right? You're going to need that information. And you don't need the sum of squares if you can find the standard error of the mean difference. Well, if you have the D column, you can easily find the mean of difference and the standard error of the mean difference. If you just look at this column and understand how to find that information from a data set. First, you got to find the difference column. All right, guys, I'm going to let you to it. We'll pause the video and see how you do. All right, guys, we're back with all the details in place. If you want to pause the video and match your work, you can. I'm going to kind of walk you through what I did. So when you do real-life studies, you collect the data, right? And here I collected the data on factory employees and what they believe are the biggest factor when it comes to well-being at the workplace. And so we have the global employees versus the United States employees. We wanted to know if their difference is that big of a difference, if there is truly a difference. So what do? You subtract them. That's all I told Excel to do. All the way down, I took global minus USA. Global minus USA all the way down. This data set right here, little d, is what I'm looking at. This data set, I want to study and see if there's a big difference in this data set from 0, right? That's our typical mu d. And my alternative would be there is a difference. So first, by the way, all I did was copy and paste this from the other example we did, because once you have it written right for a two-tailed test, just bring it with you. Bring it along with you. I just need to fill in what n was, no problem. N is 13 in this case. We looked at 13 factors. MD. Now, how did I get that? Well, that's the mean of the difference, right? Mu D, or sorry, not mu D, MD. Mean difference does mean it's the average of these numbers. Great thing about Excel, it can find the average quickly. Just go equals average of those numbers. And it is a small difference. Notice, that's a very small difference. That is, it's very close to 0. Now, what is the standard deviation of the set? S, if you're wondering. S, the standard deviation of the set. S, the standard deviation of the set. Well, you would do equals the standard deviation of the set, and you got to use dot S because this is a sample. And there's your standard deviation. Once you know the standard deviation, well, we know SMD is S divided by radical N. That's the definition of SMD, the standard error of the mean difference, is the standard deviation divided by radical N. And that's where I got that number. I'm just copying them over here. Don't need sum of squares here. That's useless information. Again, I'm copying this information into my chart. Let's just assume we're going with 5% alpha. So everything else updates nicely. There's my t-statistic. Don't have to work it again. I notice my t-statistic is close to 0, which means I'm probably not going to reject. My critical value, well, at 5% alpha, you cut it in half, 2 bars, and that's why the critical value is 21788. The good news, it updates automatically for an alpha of 0.05. P-value is still in place, but notice in the formula, it is 2 times. Yes, when you have a two-tailed test, it is 2 times. Why is it a two-tailed test? Because we're looking for a difference. We were not doing more than, we're not doing less than. We're doing a two-tailed test. That's why 2 times. And we got a p-value of 105. You want to know what? That p-value is incorrect. And the reason the p-value is incorrect is because my t-stat is negative. I want to make, the reason why I did this is I want to show you what happens if you're not careful. All right, so your t-statistic is on the negative side. Understand, the p-value is, once you have your test statistic, the p-value is the area more extreme, doubled when it's a two-tailed test. Because your t-statistic is negative, all right, because your t-statistic is negative, you actually are not going to do a 1 minus. You're actually going to do the t-dist of that value. That'll give you the area below that value, and then you got to multiply by 2. Again, the t-statistic is negative, which means we have to do t.dist to find the area below that bar. Then we got to multiply by 2 to get the total p-value, which if you notice is huge. And if your p-value is greater than alpha, which it is, then you will do not reject. My p-value is clearly greater than alpha. And that means we DNR, we do not reject. Same thing here, my T-stat is greater, not greater, my T-stat is clearly under the critical value. My T-stat doesn't come close to that critical value there of 2.17 or negative 2.17, and that's why I'm do not reject, which means I don't have, you have evidence? Nope. You do not have evidence that the difference is non-zero. The problem is there's an issue here because that Cohen's d measure is small. So there is an issue with sample size. There is a small effect size. Sample size is controlling the issue. Well, look at it. You only sample 13 people. You might have wanted, or 13 factors. You might have wanted to sample more to get your answer. But maybe there's only 13 factors to look at, so you got to be careful. In that respect, that also means your confidence interval is useless. Because if you don't reject, the confidence interval doesn't bring anything new to the game. It does give me a third check. That is, if your T statistic is under the critical value, and if your P value is too big, then that means 0 better be in the interval. Because what's going on here is you're trying to capture the true mu. And if you don't reject, you're thinking the true mu is still 0. And what number squarely lies between these two numbers? 0. All right? If 0 lies in the interval, then most likely you're not rejecting. It's kind of a triple check here. Your T-stat is less than critical value. Your P-value is over alpha. That means 0 better be in the interval. They all kind of work together to say you don't have any significant difference between you and the employees. That's really what it means. The global and the U.S. employees are really not that much difference when it comes to personal factors of success, of well-being. I do want to kind of go through this in a very general sense. Again, what did we do here? Well, we built a two-tailed t-test. All right, we built a two-tailed t-test, and we found the t-test was at critical value 218 and negative 218. My sample fell here just below average. My sample, look at your number, negative 0.07. Negative 0.07. That's your number. You are so close to average. Average is 0, remember. Here's dead average. Average is 0. I mean, negative 0.07 is just under average. How do you think you're going to get into this region, the rejection region, if you can't even get away from 0? The farther you are away from 0, the more special you are. We didn't get that far. We fell in what we call the DNR region, the do not reject region. Okay, that happens. In quality control, that's a good thing. You don't want to be in the rejection regions. It just means your sample is not significant. So as far as I could tell, the workers' opinions for global and U.S. are exactly the same. That's what I'm saying. There is no difference between global and U.S. when it comes to factors of success at the job. Sometimes it's important to draw a picture to really understand what's going on. You take your critical value based on alpha again, right? You take your critical value based on alpha. All right, this should be 0.25, 0.25 because alpha was 5%. So this is critical values based on alpha. This is your sample. Your sample did not get past the critical values, and that's why you do not reject. Now, some people really love the p-value. The p-value is all about your sample. Let's look at your sample one more time. Here's your sample. By the way, we're doing a two-tailed test. So there's also the counterpart, your opposite sample. The p-value is the probability being more extreme than your sample. It's this area. That's the p-value. The p-value is always the area more extreme than your sample. The chances of you randomly rebuilding and doing this sample again and more extreme. So the p-value will be equal to 2 because I see 2 blue regions. Now, can I find the area in this one blue region pretty easily? Sure. That's where the t.dist comes in. The t.dist says, hey, I'll find you the area in the below, all right? The t.dist, again, finds the area below. T.dist finds the area below. Notice that's the blue area, huh? Green area, blue area are matching. That's why I'm not doing anything other than using t.dist. T.dist matches this blue area. Comma, obviously degrees of freedom, comma 1. And that is why I wrote that in Excel. And look at the area. That blue area is a massive amount of the area. And so when we got a 94 or whatever it was percent, it did not shock me. Now, it might shock you, but that just tells me you're really looking at a non-significant difference. 94.6 difference, okay? 94.6% p-value. That tells me it's highly replicated, all right? You could do this easily again in another trial. There's nothing significant about the difference. If your p-value is that big, there's nothing significant about the difference. Remember, we're always reporting on the difference. There is no difference between the global and the U.S. market when it comes to the opinions and factors of well-being. And that's what I look at, all right? When you get used to the dirty details, you can spend more time on discussing. And understand, once I got these numbers, I just plugged them in. I didn't have to redo any of this math here. All this math was done out. Now, if alpha changes, it does mean I have to change my critical value. Not your p-value. Your p-value is based on your statistic. But your critical value will change. You have to change it. If you change your alpha, you have to change your critical value to address the fact you've changed your alpha. Those two are linked forever, so you got to be careful. Change your alpha, changes your critical value. They did ask one more question, and that is, all right, one of the biggest assumptions for running the t-test that you're using here, the t-inverse and the t-dist, the t-statistic, is that you have normal. How do you know you have normal? Well, the answer is I don't know if I have normal because I'm not over 30, so I can't use the central limit theorem here. What I can do is highlight the data, and I can look at the let me pause just for a moment here. Speaking too fast. I'm not in Excel, aren't I? Where's my home? There's my home. Insert good. Recommended. The box plot. Sorry, I was trying to get to it. The box plot. If the box and whiskers plot is roughly symmetric, the normality should hold true. And by adding the data labels, I can look at this difference. That's about 8 points. And this difference, that's about, 12 points? So there might be a little skew there. All right. And the mean and median. The median is -1. The mean is -0.5, -0.15, as you know here. The mean and the median, they're close but a little off. So there seems to be slight skew. So because of the slight skew, I do worry about my results. Remember, before you run all this stuff, you should run your assumptions. Are you sure you did random? Of course I did random, all right? I randomly picked workers to judge. Are you sure you have normal? The problem is we are less than 30 in sample size. That's a big deal. So what does that mean that we're less than 30 in sample size? We must check normal. How do you check normal? You check out the box plot. You check out the mean and the median. And you do other things. You do the NBP plot. There are so many tests you can run to kind of give an idea if you have normal. Well, the box plot is skewed, so I don't believe there's normality. The mean and median are slightly apart. I am worried that normal might be violated here. How do I deal with that? Well, you could trim the outliers right here. You might have an outlier. You might be able to trim that back and make it more normal. I'd have to determine if I have an outlier or not. You know, that -16, right? That -16 is a lot farther away than the -8. So that -16 looks like a huge differential there. Is that potentially an outlier? Well, you'd have to look to determine if that is an outlier or not. But I just know my results, and I am worried about the normality. So maybe there is an advanced normal test. And you might want to look into the advanced normal test to see if you truly have normal or not. If you don't have normal, what are you going to do about it with your results? Because these all become invalid if you don't have normality. So I really hope we have normality, some way of fixing that. That's a little bit pushed, I know. The bottom line, if you have two data sets and you want to look at their difference, you can. You just got to do and run the dependent t-test, as you see here. Please keep in mind, if one of your assumptions fail, that's not so good. All right, guys, thank you for watching this video. Stay tuned for others.